Okay guys, so here's unit 3, the periodic table, and this is the best unit, I think, out of the entire year. It's fun and we get to see a lot of cool reactions and some demonstrations in class. So our objectives for tonight's lesson or today's lesson would be to describe the origin of the periodic table and state the modern periodic law, and also to explain how an element's electron configuration is related to the element's placement within a period and a group on the periodic table. So we're going to figure out how periods are arranged and groups are arranged on the periodic table as well, and they are labeled on your reference table. So first, let's start with the founder of the periodic table, Dmitri Mendeleev. Was born in 1834. He died in 1907. He was a Russian chemist, and around 1871 he published his idea of the periodic table through many studies. He developed the first periodic table, arranged elements according to ascending, which means increasing. Okay, this is increasing. Atomic weight. Grouped elements by similar properties, whether it was the way they looked or the size or the shape, something like that. So similar properties, the way they reacted generally, okay, chemical or physical properties. He predicted the existence and properties of new elements, and he left empty spaces for those. So the elements that have been discovered, there were determined atomic masses, and then there were gaps between some masses. So if you see here, we have magnesium, and then at 24 atomic mass units, and then aluminum at 27. So there's a gap between 24 and 27. So he kind of he was trying to indicate that there should be something in between there. So there were spaces, not a lot of elements at the time, so we have to notice how few elements there were and that there were gaps. So obviously there were errors in his periodic table. So going a little further, about 50 years later, Henry Moseley comes along. He was born in 1887 and died in 1915. He actually studied under Rutherford. Remember, Rutherford discovered the nucleus through his gold foil experiment. So this English physicist determined the number of positive charges, or protons, in the nucleus by measuring the wavelength of X-rays given off by certain metals. By that, he was able to develop the first concept of atomic number. And remember, we learned last unit that atomic number defines the element. And that's basically what Henry Moseley did. If we know the number of protons, we then know the atomic number, and we can look that up on the periodic table and figure out what element it is. Alright, so the modern periodic table is arranged by atomic number, and we now know that, and thanks to the work of Mr. Moseley. And there he is right there. Not a great picture. So chemical periodicity, or the history of the table. So the word periodic means cyclic or repeating patterns or cycles, similar to a monthly or weekly calendar, days of the week. So you could say that the periodic table is a calendar of the elements. So for example, this would be your cycle: tired on Mondays, happy on Fridays. It's the end of the week. Same idea. Okay, it's a repeating pattern. So to sum up, we have Dmitri Mendeleev from Russia, first chemist to arrange newly found elements into a table form and a usable manner. And then it was built off of that. Okay, so he was the foundation. Elements arranged according to atomic weight, and this resulted in gaps or periodic intervals being out of order. So there were errors and wasn't going to be the best table to use. And since it was the earlier version, and we now know we're still finding new elements, we need to leave those spaces there. So Henry Moseley, again, we have an asterisk here because he is the founder of the modern periodic table from England, arranged the table by atomic number, or the number of protons, which proved to be much, much more effective. Ooh, effective. Okay. How the modern day periodic table is arranged. So the periodic law, this is one of our objectives for this lesson, and we need to memorize this one right here. Elements in the periodic table are periodic functions, repeating functions of their atomic number. So in other words, this is saying that everything is in order based on their atomic number, and properties will relate back to the atomic number of that element. Okay, so we have all of this. Again, I'm just reiterating that for your purposes. And so the arrangement of the periodic table begins with periods, and they're horizontal rows, okay, that run left to right on the periodic table. So this would be period 1 or 2 or 3. Okay, it starts at 1, goes all the way across the periodic table, and then goes down to 7. All right, so there are a total of 7 periods or rows. The number of the period tells us the number of electron shells, or principal energy levels, or principal quantum levels, as we discovered in the last unit, that the Regents likes to use that word quite often. Quantum, same thing as energy. Okay, number of valence electrons increases from left to right. So going from 1 to 8, K is in period 4. Properties of elements change drastically across a period. So as we go all the way across the periodic table, we see properties change a lot. Okay, so we're going from metals and then metalloids and semi-metals to non-metals all the way over on the right-hand side of the periodic table. And we'll talk about groups and families later. So again, the number of valence electrons increases from left to right as we go across the periodic table. Groups. Okay, so now these are the vertical columns. There's 18 groups, 18 total groups in the periodic table, and each group contains the same number of valence electrons and similar, not identical. Okay, so I'm going to underline that, not identical chemical and physical properties. So what this means is that they react similarly. They might have the same type of physical or similar type of physical properties, soft, malleable, ductile, things like that, but they will not be exactly the same because they have different number of valence electrons, so they are going to react a little differently. So let's look at Lewis dot diagrams or electron configurations for elements in the same group. So groups are going down, okay, so we're talking about columns, and group 1 consists of hydrogen, which is kind of separated from the periodic table, lithium, sodium, potassium, rubidium, cesium, and francium. These are all metals, all reactive in water. I'm going to do a demonstration on Monday to show you how some of these metals react and how their chemical properties change as we go across a period or down a group. So here I labeled the periods that each one of these are located in. So hydrogen is in period 1. Notice one valence electron. Okay, it only has one electron. Lithium, one valence electron. Sodium, one valence electron. So what I did was I just copied the electron configurations down off of the periodic table. Remember, francium, okay, has 7 principal energy levels, and we shorten the address for the electrons by kind of skipping the 2-8. So that's what this little asterisk is telling us. Okay, the 2-8 still exists, it's just a condensed version on the periodic table, so we have to consider that. 2-8 are the first 2 numbers, then 18, 32, 18, 8, and 1. So there are 7 energy levels, 1 being on the outermost energy level. Okay, remember, the most energy will always exist in that valence shell. Doesn't matter how many you have, it still will have the most energy on the outside. So we have to look at the similarities that we can see within the above electron configurations. And we're going to look at it again. So yeah, there is a trend. All have one valence electron. The group number, okay, this is group 1. Group number is equal to the number of valence electrons. And the period number, okay, as we go across, is equal to the number of principal energy levels or quantum levels. Notice, okay, 1, 2, 3, 4, 5, 6. All of the elements in that period will have 6 energy levels. Okay, if we go to group 2, all of the elements in group 2 will have 2 valence electrons. All elements, I'll give you another example, all elements in group 13 have 3 valence electrons. So I'm going to show you in class what I mean by this. Okay, there is a transition between groups 3 through 12. Okay, and they are exceptions. Skips over to 13, 14, 15, 16, 17, and 18. Okay, and then so what happens is a way to indicate valence electrons this way is that we just look at the last number, because 3 through 12 are skipped over, and we'll talk about that later and why. Okay, but 13 tells us that 3 valence electrons. 4, all of the elements in group 14 have 4 valence electrons. All of the elements in group 15 have 5 valence electrons, and so on, all the way up to 18, group 18, where there are 8 valence electrons. So this would be neon and argon, okay, noble gases, krypton, and I could keep going, but those are just some examples. So, octet. This means an oct. The prefix oct means 8. All right, this indicates that there's a full valence shell, which means 8 electrons, except for period 1 elements. So all of the elements that have octets, those would be the noble gases, okay, completely full outer shells, 8 electrons, and the exceptions are hydrogen and helium, because they only have 1 valence shell and they can only hold up to 2, okay, not 8. So we are going to just say for now that 8 electrons except for period 1. So anything that has a full valence shell, meaning 8, okay, stable octet. So when it is a stable octet, these elements are non-reactive, basically antisocial. They don't like to mix with anything. And finally, this is our last slide. I'm just showing you a modern periodic table, okay, and it's grouped according to chemical properties and physical properties, and the colors indicate what groups these elements belong to. So This one, okay, all of the elements that are yellow are noble gases, and I just discussed those. And we're going to get into more detail about each type or class of elements. Okay, all of the red are nonmetals. Nonmetals. All these two groups, okay, these are metals, but then there are two different types. There's the first row, or the first group, are alkali. Okay, so alkali. And then there's alkaline earth, which are group 2. All of these are transition metals. And the word transition means to kind of shift, right? To go from one type of property to another, transition from one place to another. Okay, so that's what's kind of happening as we go across a period, the elements' properties are kind of transitioning into a different type of element or class, okay? So metals, and then there's still transition metals. They might have some properties of some non-metals possibly as they go across, okay? So transition metals, and these are exceptions to the rule of valence electrons, all right? And then we have our metalloids, and which have properties of both metals and non-metals and non-metals. Right? And then hydrogen is out here considered a metal because it's on the left-hand side of the periodic table. And that's it, okay? Please check out Quizlet for the vocab. It's not on the front page of your guided notes, but I set up a guide for you for Unit 3 vocabulary, okay? And that ends our lesson tonight. Thank you, guys.